So today we're looking at basically this lesson is scientific notation. So maybe you've heard of that before. It's used a lot in science classes, and really it's just a different kind of format. So if you look at this box here where we're discussing scientific notation, look at the first example right here. That number is 6,700,000,000. That's the number. But sometimes we don't want to write out that because it's such a large number. So scientific notation is a way to condense a number, either a really big number or a very small number. And so how you do that is you look for the decimal point in the number. So this is a whole number. So it would have a decimal point at the end of the number right here. And so the goal is to move the decimal point however many times necessary in order for you to get a number between 1 and 10. And that's what I wrote here. It's scientific notation is just a different format where you're expressing a number between 1 and 10. So I have to move this decimal point 1, 2, 3, 4, 5, 6. I'm continuing because at this point, the number would be 6,700. It is not a number between 1 and 10. So 7, 8, 9, and this is where I'll stop. You see, when I put the decimal point there, I'm getting the number 6.7. And then this piece right here is part of scientific notation. You're multiplying by 10 and you raise it to whatever power it is based on how many times you move the decimal point. So you see how I moved the decimal point 9 times? That's why that's a 9. So this is the amount of times the decimal point was moved. I'll just say the decimal was moved. And I know it's going to be a positive 9 because I'm dealing with a very large number. So let's also write here, large number equals positive exponent. So let's look at this other example below it. It's a very small number. That is not in scientific notation because it's not a value between 1 and 10. So again, we're doing the same procedure. I'm going to move the decimal point however many times I need to in order for me to get a value between 1 and 10. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and I'm going to move it one more time, 15. That gives me 2.0 or 2. And then notice here, it should be 10 to the negative 15 as an exponent like that. The reason why it's negative, this is a small number, and small number means negative exponent. That's how I remind myself if the exponent will be negative or positive. Okay. So let's go ahead and look at this review of rounding here. So it says round the following numbers to the nearest 10th and then also to the tens place. So we'll do maybe 1 or 2 to see if we get the hang of this. Let's say I'm doing part A, the nearest 10th. So if you're looking at 6.34, the number in the 10th place is a 3. So if the rule of rounding is you look to the right of whatever number you're concerned with. In this case, it's the 10th place. Look to the right of that. If the number to the right is 5 or greater, then you'll round the number in the 10th place up 1. But in my case, the number to the right is 4, which is not a 5 or greater. So rounding to the 10th place would just be 6.3. You keep that value. Part B, tens, TENS. right? There's a difference between tenth with the TH and tens. When we think of tens, we look at, 0, 10, 20, 30, 40. You're going by tens, right? Whole numbers. So look at the whole number now. The whole number is 6. Here are my options. It's either going to be 0 or 10. But 6 is closer to 10, so my answer would be 10. 6.34, if I had to round that to the tens place, would be the whole number 10. It is closer to 10. In the same way, let's look at number 2. We want to round it first to the 10th place. So currently in the 10th place is the 2. And then you want to look to the right of that. To the right of that is a 4. So I'm going to keep this as 98.2. You only round up if the number to the right is 5 or greater. And then rounding to the tens place, 98 can either go 2 ways. It can either be 90 or 100, right? 98 is closer to 100, so that is my answer. And the last one there. Rounding to the 10th place, 356.7. And then if we're going to round to the tens, let's look at 356. Here are my options, 350 or 360. You're always thinking in terms of 10, right? 350 or 360. So obviously 356 would be closer to 360, and that would be my answer. We're introduced to another type of really format, which is called significant digits. And if you kind of just peruse below at this table, there's a lot of rules involved with determining how many significant digits a number has. A lot of it has to do with zeros and where they're placed in the number. And I really don't want you guys to memorize those rules. So I'm going to show you how you can figure out the significant digits by using something that we already discussed, which is scientific notation. So instead of memorizing this table, I'm going to show you how to determine significant digits, but through scientific notation. So let's look at this next example. It says, state the number of significant digits and the implied precision of the following numbers. So let's look at the first thing. It says state the number of significant digits. Let's focus on that. So currently, part or letter A, 0.003 is not in scientific notation, right? I know a number is in scientific notation because it has to be a number between 1 and 10. And this is not, right? It's less than 1. So my first step when it asks me for the number of significant digits, I'm going to put that number into the scientific notation. So to do that, I move the decimal point however many times I need to in order for me to get a number between 1 and 10. So that means 1, 2, 3. And if I do that, then I'm getting 3 times 10 to the, it's going to be a -3. Remember, I moved it 3 times, but how you know if it's a positive or negative is if you're dealing with a big or a small number. Remember I said here, I'll highlight it for you, large number, positive exponent, small number, negative exponent. That's what you want to be reminded of. So this was a small number, so it's a negative exponent. Now that I have it in scientific notation, the number of significant digits is however many digits is in this number right here. There's only one number, or I'm sorry, one digit. So my answer is 1 significant digit. I'm just abbreviating that. It's also asking us for precision. Precision means how detailed your number is. So we're looking at to what decimal place was the original number. So it was 10th, 100th, 1,000th. So the precision is to the nearest 1,000th. You're just looking at the original number and looking at to what decimal place is it at. B, we don't need to put in scientific notation because it's already a number between 1 and 10. So here I'm just simply counting 1, 2, 3, 4. There are 4 significant digits because there are 4 values there. So that's the significant digits. And then it asks for the precision. Again, to how many places is this rounded? 10th, 100th, 1,000th. So again, the precision is to the nearest 1,000th. For the next one, we have 350,000. That is not a value between 1 and 10. So in order to state the significant digits, I'm going to restructure this, like reformat this number by putting it in scientific notation first. So here is my decimal point. I'm going to move it over as many times as necessary until I get a number between 1 and 10. So that's 1, 2, 3, 4, 5. That gives me 3.5, right? Times 10 to the, I moved it 5. And it's going to be a positive 5 because 350,000 is a large number. Now, to determine the significant digits, just look at how many digits is in this value. And my answer is 2, 3 and 5, that's 2. 2 significant digits. And precision would be, well, what decimal place or what place value does this number hold? So this is ones, tens, hundreds, thousands, 10,000s, 100,000s. 350,000 is in the 100,000s. And the last one, D, it is not a number between 1 and 10. So my first step is to put this into scientific notation. So 1, 2, 3. I can stop there. So that gives me 4.502 times 10 to the, I moved the decimal point 3 places. It was a small number, so it's -3 exponent. To determine the significant digits, look at how many numbers are in this number. That's 4. So 4 significant digits. And again, the precision is looking at the place value. So this first 0 after the decimal point, that's the 10th, 100th, 1,000th, 10,000th, 100,000th, and then millionth. So we're at the nearest millionth. That is the precision. Let's look at the next example. So it says, carry out the indicated operation and give your answer with the specified number of significant digits. So what they want us to do is just do this operation, meaning multiply here, and then we just want our final answer to 5 significant digits. So let's go ahead and do that. So if I do 386 times 43.2, if I just multiply that, my answer is 16,675.2. So now they only wanted to have 5 significant digits. You see, I have 6 values there. So remember I said the shortcut here is, well, there's 2 ways you can do this actually. You can just look at, okay, well, if I were to round this to just 5 numbers, what would that be? 16,675.2 to 5 digits is 16,665. Let's do this operation, 345 divided by 0.36. When you do that, your answer is 958.33. The 3 is going to continue to repeat on. So to 5, so I'll do this. The 3 will continue like that. So to 5 significant digits, make sure you have the 5 values there. That would be 958.33. The next set of examples is we're going to talk about different types of error. And the two that we'll cover are random error and systematic error. So what random error is, basically, just like the name implies, it's an error that you couldn't predict. It was random. So I'll just circle this. Random errors occur because of random and unpredictable events in the measurement process. Systematic error, it's the opposite. It occurs when there is a problem in the measurement system that affects all measurements in the same way. That's what makes this type of error systematic, because it's not just randomly happening here or there to just a few measurements. There is an error occurring in all your measurements in the same way. That's what's the difference between random error and systematic error. And then I provided an example for systematic error, such as making all the measurements too low or too high by the same amount. This is what we call systematic error. So what I wanted to do was just look at a few of these, and if we can determine whether this type of error is a random error or a systematic error. So let's look at part A. So number 1, suppose you work in a pediatric clinic and use a digital scale to weigh babies. The baby is not holding still on the scale, which causes the weight to be anywhere from 14.5 to 15 pounds. So let's pause there. We want to know, is that error considered random or systematic? And so here I would say, because the baby is shaking on the scale, right, not holding still, it doesn't say that this is happening to all the measurements, meaning all the weights in the same way, right? It's just random if the baby is not holding still. So this would be considered a random error. So number 1 is a random error. I'll put here any measurement can be too low or too high. It's not all, right? It's just random. And let's look at the second part 2. Now suppose you have weighed babies all day. At the end of the day, you notice that the scale reads 1.2 pounds when there is nothing on it. So we want to figure out what kind of error is going on here. Well, if the scale weighs 1.2 pounds when there's no object on the scale, that means every time you've put a baby on the scale, that baby's weight automatically has increased by 1.2 pounds, right? Because there was an error going on, and that error was the same with every baby because the scale was off by 1.2 pounds. So this would be considered a systematic error. And so I'll write here, all measurements were increased by 1.2 pounds. And this is what makes it systematic. I'm going to skip B because I didn't finish this, but let's do C and D. Before taking off, a pilot is supposed to set the aircraft altimeter to the elevation of the airport. A pilot leaves San Diego, the altitude is 17 feet, but her altimeter is set to 517 feet. Explain how this affects the altimeter reading throughout the flight. So we want to figure out, is this a random error or a systematic error? So the aircraft altimeter is supposed to be set to the elevation or the height of the airport, right? Which the pilot is leaving from San Diego, so it should be 17 feet. However, the altimeter was set to 517 feet. So now the altimeter readings will be affected, right? There will be an error throughout the whole flight. But we need to determine, is that error a random error or is it a systematic error? And so the answer here is this would be a systematic error. And when you're looking for systematic error or determining if it is systematic, you're looking at, is the same error going to occur to all measurements? And in this case, yes, all of your altimeter readings will be increased by 500 feet. Because remember, it should be 17 feet, but instead the altimeter reading is currently 517 feet, which means it's increased by 500. So because of that, as you continue on in the air, all the readings will be 500 feet too high. And so this is systematic. So I'll say here, all altitude readings will be 500 feet too high. In 2015 and 2016, a mosquito-borne disease called Zika fever spread through much of the Americas and a few other areas of the world. Researchers studying the progression of the Zika epidemic faced at least two major challenges in determining how many people had been infected. Some people who were suffering from the Zika infection were misdiagnosed as having other diseases, and vice versa. And then two, many cases of Zika infection occurred in poor or remote areas where medical diagnosis was not available. So let's look at those two scenarios. First, let's look at number one. What kind of error is this? Random or systematic? So it says some people who were suffering from the Zika infection were misdiagnosed as having other diseases. Because it says some people were misdiagnosed and not everybody, right? This would be considered a random error. I'll say it was unpredictable misdiagnosis. And let's look at scenario two. Many cases of Zika infection occurred in poor or remote areas where medical diagnosis was not available. Now, here's a different scenario. There was, medical misdiagnosis again, or I'm sorry, medical diagnosis was not available, not misdiagnosis. The diagnosis wasn't there, but why? To poor or remote areas. So in this instance, all people in poor or remote areas did not receive a medical diagnosis, right? It wasn't available for anybody. So this is considered systematic. And so I'll write it like this. This affected all remote areas. And so all the people in the remote or poor areas. So now that we've identified these two errors, we can actually quantify it, meaning giving the size of the error. So I want you to look at these two types of errors as far as size goes and see how similar they are to what we talked about last week. Remember when we were doing the section on percentages, we had absolute change and relative change. And absolute change, I just shortened the formula to new minus old, right? And new minus old divided by old, there was the formula. Now we're talking about absolute error and relative error. Same concept, except we're dealing with error now, but there's still an absolute and a relative. And the absolute just means you're taking the difference. But now I'm not saying new minus old. We're talking about the measured value minus the true value. That is the formula. Measured value minus true value. Relative error is measured value minus true value divided by the true value. And then remember, we always either multiply by 100 or move the decimal point 2 places to the right, because we always want the relative error or the relative change, whatever we're looking at when it says relative, you always want that to be a percentage. Okay, so not much different. It's just now we're not talking about a new value and an old value. You're talking about a measured value, what I measured, minus true value. And then relative error, measured minus true divided by true. So let's look at a few examples of that. It says, find the absolute and relative errors. So it says your true height is 1.73 meters. And then I give it in feet and inches, but you don't need that. And a nurse in your doctor's office measures your height as 1.76 meters. So we want to find the absolute and the relative error. So let's start with absolute error. And the formula for absolute error, remember, is, I'm going to slide up here so you can see it, measured minus true. You can memorize it like that, measured minus true. So the measured height is the one that the nurse measured, right? Which is 1.76. Measured minus true height is 1.73. And you're just taking the difference between the two, and that's 0.03. That is your absolute error. And then we have relative error. Relative error, again, is measured minus true. So we just did that, measured minus true divided by true. And so on the top, if I subtract that, that's 0.03 divided by 1.73. So if you divide that on the calculator, you're getting 0.0173. We want to make that a percentage for relative error. See, I circled percentage here. You always want the relative error to be a percentage. So move the decimal point 2 places to the right and add the percent sign. So that's 1.73%. Okay, let's look at the next one. It says the label on a bag of concrete says 60 pounds, but the true weight is only 58 pounds. So we want, again, the absolute error and the relative error. So let's write absolute error. The formula for that is measured minus true. Measured here is 60 pounds. And then you see true weight is 58. So measured 60 minus true. That equals 2. Relative error formula is measured minus true divided by true. So that's 2 on top divided by 58. And if you do that on the calculator, you're going to get the decimal, right? So 2 divided by 58 is, you should get 0.03, let's say 4. And we want to make that a percentage. So we're going to move the decimal point 2 places to the right and add the percent sign. And let's look at the last one. The actual distance to the destination is 46.7 miles, but your odometer reads 45.8 miles. We want to know the absolute error and the relative error. Absolute error is measured minus true. Your odometer is what you're using to measure, right? So this would be considered measured. Good. Measured minus true. And if you subtract that, you should get negative 0.9. And it's okay if it's negative, right? That makes sense. You're doing a small minus bigger number, so you'll get a negative. That's okay. And then relative error. That is measured minus true divided by true. And so on top, we know we get negative 0.9 because we just did that. And when you divide the two, you should get negative 0.019. And again, we always want to make the relative a percentage. So let's move the decimal point 2 places to the right. And that's negative 1.9%. The last thing I want to talk about today is when we have results, we can identify if they're accurate and precise. And so I want to talk about what that means. If something is accurate or has accuracy, you're looking for how closely a measurement approximates to the true value. So really, I'm looking at how close it is to the true value. I'll say to the true value. That's all you're looking at when you're saying something is accurate. It is very close to the true value. Whereas precise, we're looking at the amount of detail, meaning how is it rounded? Rounded. And how that relates to the true value. So accuracy, you're looking at how close your value is to the true value. And precision, you're simply looking at how detailed, how rounded your value is. So let's look at these last two examples here. Suppose your true weight is 102.4 pounds. The scale at the doctor's office, which can only be read to the nearest quarter pound, says your weight is 102.25 pounds. The scale at the gym, which gives a digital readout to the nearest 0.1 means 10th with a TH. To the nearest 10th pound says your weight is 100.7 pounds. Which scale is more precise? Which is more accurate? So I'm going to write it down like this. We have three things here. It says your true weight. So let's write that. True weight is 102.4 pounds. And then you have the doctor's scale, let's call it that, the doctor's scale, the scale at the doctor's office, which is 102.25 pounds. And then you have the gym scale. And the gym scale reads 100.7 pounds. And so the question is, comparing your true weight, right? Knowing your true weight, which scale is more precise and which is more accurate? So think about what accurate means. Let's address that first. Accurate, we're looking at which result is close to the true value. So looking at both gym and doctor scale, which one is closer? 102.25 is closer to 102.4, so this would be considered accurate. And I'm just going to put here closer to true weight. That is how you determine which is accurate, which one is closer to the true weight. Now, precise. With precise, we are looking at the detail, how it's rounded, and comparing that to the true value. So the one with the most detail that's closest to the true weight as far as detail and rounding goes would be the Jim scale. This would be precise. And the reason why is because Jim scale and true weight are both rounded to the 10th place. That is why the Jim scale is more precise. You're just simply looking at the rounding. It says your weight is 52.55 kilograms. The health clinic scale gives weight measurements to the nearest half kilogram. And so your weight is 53 kilograms at the health clinic. And then a digital scale at the gym gives the reading to the nearest 100th kilogram. So your weight is 52.88. So again, let's organize this. My true weight, right, is 52.55 kilograms. The health clinic scale has our weight at 53 kilograms. And the gym scale has your weight at 52.88 kilograms. So again, we want to know, let's do which one is more accurate. 2.88 is going to be closer, right? If you subtract 52.88 minus 52.55, you're getting less than 0.50, right? 52.88 minus 52.55 is 0.33. That is closer than 53 minus 52.55. So this is more accurate. This is closer to the actual weight. And also this one happens to be more precise too. And I want to show you that. This is rounded to the 100th place, right? And so is your true weight. It is rounded to the 100th place. So the Jim scale is, and I'm going to write an explanation here. It's more accurate because it's closer to the true value and rounded to the same amount of decimal places as the true value.